When it comes to drawing electric fields, the method is not drastically different from drawing gravitational fields. And because of that, I'm going to show you the connection between gravitational fields and electric fields. If you understand gravitational fields well, electric fields will be no problem at all. So just to quickly recap what we've spoken about previously, if I want to test a field, I have to use some kind of particle. If I'm talking about a gravitational field, I'm going to use masses because a gravitational field will attract masses or will exert a force on masses when placed in that field. So if I tested the gravitational field around Earth by placing masses, in each case these masses would be pulled towards the center of the Earth. Therefore, if I wanted to draw the overall gravitational field around the planet Earth, it would look like this. And these arrows point inward because no matter where I placed a mass, that mass would be pulled towards the center of the planet. Now, it's been a little while, but it's important to remember that those field lines represent the force that will act on a particle, in this case mass, when it is placed in the field. And that becomes really important to remember. So some of your notes jot down that the field lines represent the force that will act on a particle when it's placed in the field. In the case of gravity, it's a mass. In the case of electricity, it would be a charge. Now here's the problem with the electric field. If I had a positive charge, okay, so some positively charged object, if I placed a positive charge here, it would get repelled. That's fine. But if I placed a negative charge, it would be attracted. So we run into this problem because which way should these field lines go? Because they could technically go either. And that was one of the problems they had about 250 years ago. And in order to alleviate this, scientists got together, basically said, let's just all agree on one. This way, when we speak about it, everyone will be on the same page. So while either one could technically be used to detect the presence of an electric field, it was ultimately decided that scientists, engineers, will use what is known as a positive test charge. It's not a real charge, it doesn't exist, it's just like a concept. And that positive test charge is just the tiniest, smallest possible amount of charge that has a positive value. So if I wanted to test the field conventionally, as scientists would, around this positive charge, I would place a positive test charge, let's say at this location, and that would get repelled because two positives will repel. If I place that positive test charge here, it would also get repelled, and so on and so forth. Therefore, if I wanted to draw the electric field around the positive charge, remember the field lines represent the force that will act on a particle, in this case a charge, a positive test charge, when it's placed in the field. Therefore, the field around this positive charge, all these arrows should be pointing away, because no matter where I place this positive test charge to test the field, it will be repelled by a positively charged object. Similarly, if I had a negatively charged object, it doesn't matter that the object itself is negative, I'm still going to test this using a positive test charge. No matter where around this negatively charged object I place this positive test charge, it will always be pulled towards that charge. Therefore, the electric field around a negatively charged object would look like this, very similar to the positive charge. However, the arrows point inward because a positive test charge will be repelled no matter where you place it around a positive charge and will be attracted to a negative charge no matter where it's placed. Positive and negative charge by themselves, not too bad. Things get a little bit trickier when we're talking about multiple charges. When you have something like this, where you have a positive